So students, as a follow-up session, I want honest, prompt replies from you about the questions which I will ask. If you remember, I asked you to by heart, you can say, or use any trick and work to remember the few elements and their atomic number. Prathamesh, you want to say something? You raise the hand.
Sir, there are messages in group that link is not opening.
Message in the group. Saurabh is saying, Saurabh joined now. Whoever said no, link is not opening, he's in the class. Yes, Saurabh, what is the problem?
Yes, sir.
Link was not opening.
Yes, sir. कालची लिंक ओपन झाली.
Okay. Let me see that link. Just let me confirm. Because what happens if any alphabet also doesn't go there, no? Then also that issue may pause. Yes. Last one alphabet, that's a Z is not there. Z is not there. In the link, whatever I sent, no, in that Z is not there. That one letter was missing. Actually, link is same. I am using the classroom. Last year, I remember Prathamesh said that let we use a common link. So now I got this that opportunity from Google Classroom. I come to know that directly for this class, no, we can prepare a classroom. This whatever we are preparing, no, here. So the same link remains there. Continuation. That Z was missing. Okay, maybe because of that few have not joined. Yes, Saurabh. Because of you, I came to know, no, that mistake took place. Thank you, Saurabh. Yes, Prathamesh, thank you also. You reminded that other students were not joining because of that. Those who used the previous link, they could join. Now I put the message there. Okay, yes, Gauresh has changed that. Yes, Gauresh, thank you very much. Okay, good, very good. Yes, you are the very brilliant students. Okay, students, what I was saying, we have to take a follow. And now I will take a follow for your work. I will ask the element from first and second transition series. You have to tell its atomic number. Or I will ask atomic number. You have to tell the element. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Mandar.
Yes, sir.
And Shilpa. Shilpa has just joined. Shilpa, we are taking follow-up session now. Yeah. So I will ask that particular student and the student has to reply. Expected that you should not open the periodic table. Means because we are checking here, no? How far you have remembered that. After all, it depends on your honesty. Yeah. Mandar, I start with you.
Yes, sir.
Chromium, atomic number.
24.
Good. Yes. Prathamesh, ruthenium, atomic number.
Sir, repeat.
Ruthenium, atomic number. Ru.
44.
Good. See, 24 and now here what the 44. Shilpa, I want the element name whose atomic number is 47.
Don't know, sir.
You have not worked. See, 47. Have you worked to remember the names, Shilpa? Means you worked, but now you do not know, or you have not worked for that. Yes, Shilpa, may I know the reply, please?
No, sir.
Means you have not worked. Okay. Now, next time I want your work. Means this first two transition series. By the way, one more transition series is coming for the next revision. Is it clear?
Yes, sir.
Yes. Who will answer the question of Shilpa?
Silver.
What is that?
Silver.
Right, silver, 47. That's a silver, a very important element from ornament preparation point of view. Yes, the element zirconium. What is atomic number? Saurabh, will you answer?
40.
Is it 40? Good. 40. Zirconium, 40. Yes, now the next question is to Shubham. Shubham, are you ready?
Yes, sir.
Yes. I want the name of the element whose atomic number is 46.
Palladium.
Right, palladium. PD. Good. Now, Gauresh, question to you.
Yes, sir.
Very good. Very prompt reply I found. The molybdenum is one element. What is its atomic number?
42.
Good. 42. Brilliant. Now, fastly. Suppose if I tell you name, no, that student will say that element. Then next student will pronounce next element. For example, if I ask Prathamesh, then answer is manganese. The next element, I'll put the name. Mandar will say iron. Saurabh will say cobalt. Shilpa will say nickel. Shubham will say copper. And Gauresh will say zinc. Means continuity of the elements I am talking about. Means atomic number 1 decided. Now next element. Is it clear now?
Yes, sir.
Yes. So Prathamesh, I want the element with atomic number 21.
Scandium.
Shubham, next element.
Titanium. 22.
Very good. Mandar, next element.
Vanadium.
Very good. Shilpa, next element.
Chromium.
Very good. Saurabh, next element.
Manganese.
Yes. Gauresh, next element.
Iron.
Very good. Very good. Prathamesh, next. Prathamesh thought that my turn is over. Prathamesh, after iron, which element?
Cobalt.
Yes. Shilpa, next element.
Nickel.
Gauresh, next element.
Copper.
Mandar, next element.
Zinc.
Yes. Next element with atomic number 39. Shubham.
39 yttrium.
Yes. Saurabh, next element.
Zirconium.
Prathamesh, next element.
Niobium.
Mandar, next element.
No, sir.
Okay. Saurabh, next element. After niobium.
Molybdenum.
Good, good. Shilpa, next element. Shubham, next element. After molybdenum.
Technetium. Technetium.
Yes.
43.
Very good. Gauresh, next element.
No, sir.
Mandar, next element. After technetium.
Rubidium.
Not rubidium. It's a ruthenium. Ruthenium. Rubidium is RB. It's RU. Ruthenium. Prathamesh, next element.
Rhodium.
Rhodium. Right. Shubham, next element.
46 palladium.
Right again. Second time is asked. Gauresh, next element.
Silver.
Very good. And last, Mandar, will you end? Last element in the second range series.
Cadmium.
Good. Very good. Very good. No problem. I'm happy to know that at least you have started to work, and those who have not worked or partly work, I expect from them more good performance next time. Shilpa, is it clear?
Yes, sir.
Yes, and other students also have to work. So,
Yes, sir.
is this revision clear? Concept? Somewhat
Yes,
because of
sir.
that. At least I come to
Yes, sir.
know who are spontaneously replying, who have worked, who have studied, and who have not. Or possibilities are there. You have studied, but now you could not able to recall. Means you have not studied. So what to do for that? Revision is important. You train your brain. Training a brain is a very enjoying process only because of our interest and all those terms, no, we have kept the things aside. Challenges are to take, and you are the challenge takers. Brilliant, very good. So students, shall we go to the next point now?
Yes, sir.
Yes, sir.
Next time I will ask one more series. Means these two series will be there. First set transition series, second transition series, and one more transition series. That's a third transition series will be there for discussion. Means it is the sixth period. Those elements will be there for the discussion. Means how we revise, no, then afterwards, whatever the lecture I conducted later, no, after the after element electronic configuration. So electronic configuration point also will be involved, and oxidation states if needed, or I can keep oxidation state for the next lecture for the revision. I repeat, students, next time means next lecture I will ask you question regarding the elements and atomic number of first three transition series is a one part. Second part, electronic configuration of first transition series elements. Is it clear?
Yes, sir.
About oxidation state and all we will discuss.
Yes, sir.
Yes. Now, last time, whatever the discussion we did, it is with me. Okay, now started the screen presentation. I start the presentation. Yes, could you able to see the screen?
Yes, sir.
Yesterday is our role task.
Yes, sir.
Yes. We have discussed yesterday oxidation states of first transition series elements. Those are variable. Example for oxidation state I had given. That's a sodium, which carries +1 charge. Calcium, +2 charge. Fixed oxidation states. But in case of transition series elements, right from the Mn+2 to Mn+7, wide range of the variation in the oxidation state is there. During range, what is the minimum oxidation state? Minimum oxidation state is equal to number of electrons in 4s orbitals. I am talking about these first transition series elements, and maximum oxidation state is equal to that number is there plus number of unpaired electrons in 3d orbitals. And not only this formula we discussed, we applied this formulae and we come to conclusion. Scandium can show +2 and +3, titanium can show +2, +3, +4, vanadium +2, +3, +5, chromium +1, 2, 3, 4, 5, 6. If you note clearly, see here 3, 4, 5, 6, and then 7 for manganese. After manganese, what will happen? The maximum oxidation state will go on decreasing. Here one more element is there in between. After manganese, which element is there?
Iron.
Iron, yes. So it's maximally plus 6. So plus 7, plus 6, plus 5, plus 4, plus 3. Likewise, decrease will be there. Means it's a like a pyramidal variation. Means if I consider this as a base for the pyramid, here will be the increase and then the decrease. Means such kind of the conical arrangement, pyramidal arrangement. So pyramid of oxidation states we have discussed yesterday. Minimum oxidation state generally is plus 2. Exceptions are there, chromium and copper, where you can find plus 1 as a oxidation state. When we find such a variable oxidation state, different oxidation state, then question comes about the stability. Which oxidation state is more stable? It is found by study that tri-positive oxidation state, tri-positive metal ions are more stable compared to dipositive, compared to other oxidation states. It is a general statement. It is not a particular statement. Question arises, then on which factor this oxidation state stability depends? For that, in your syllabus, they have included electronic configuration point as a first explanation point. It is not the perfect explanation, but the first explanation. So I had given you example of manganese plus 2 here, manganese plus 2 and manganese plus 3. For manganese plus 2, D5 is electronic configuration. For manganese plus 3, D4. D5 is a half filled electronic configuration, completely vacant, half filled and filled. These orbitals govern extra stability. Therefore, Mn plus 2 is more stable compared to Mn plus 3. One more example, ferrous Fe plus 2 and ferric Fe plus 3. Ferric has D5 electronic configuration, stable electronic configuration. Therefore, ferric is expected to be the stable compared to ferrous. This is a general. Likewise, you can give many examples. You can give example of scandium plus 3. You can give example of Zn plus 2. You can give example of Cu plus, but there exceptions are there. Cu plus, as per electronic configuration point, it should be more stable. But what is the reality? Cu plus 2 is more stable. So conclusion here is electronic configuration is the perfect concept by which we can understand the stability of the oxidation state. Then the perfect concept is in the thermodynamical understanding, energetic variation, concept of energy investment, energy needed, and energy output, means energy which comes out. Then wherever energy is needed for solvation energy, sublimation energy, energy is needed. For ionization energy is needed. For solvation or lattice formation, energy will come out. Combination of all those three factors, these are thermodynamic factors, will decide the Gibbs free energy change, or will decide the fate of that, the conversion or the transition or the formation of oxidation state. What we expect? We expect profit. When will we get the profit? When more energy will come out compared to investment, compared to absorb. It means when solvation and solvation energy or lattice energy will be more and more, then that state can be the more stable, because sublimation energy is comparable. That first factor is there, no, it is comparable, means it is nearly same. There is a no lot of difference in sublimation energy. Ionization energy can vary, because to form plus 2 ion, only 2 electrons you have to remove. To form plus 4 ion, you have to remove 4 electrons. To form plus 7, you have to remove 7 electrons. So work quantity varies, so amount of energy needed will certainly vary. So ionization energy, the point is there that we need to what? Consider here. It varies. For ionization, as more energy needed, more positive ion will form. But by the way, think about the third factor. More the charge on the cation, more will be the lattice energy. Last semester you have studied F.Y.B.Sc equation, Born-Landy equation, lattice formation. So that lattice formation, lattice energy depends upon charges. So ionization, there are more investment, I agree. But by the way, because of that more investment, more profit also you will get, more solvation energy you will find, more lattice energy you will find. So it's a matter of reality. It is not the fact that always higher is the charge on the ion, more will be the lattice energy. Combination of all will decide the stability. That's a correct answer for the stability of oxidation state. Only electronic configuration cannot explain, but at the beginning level, electronic configuration certainly can help us to decide the stability. Therefore, that point is included in your syllabus. So, conclusion we have sought out that explanation for stability of oxidation states of transition element we can discuss on the basis of thermodynamic considerations. Three thermodynamic considerations are there. Will anybody help me? Which three thermodynamic considerations are there?
Sublimation energy,
Yes. Second.
Ionization energy.
ionization
Third.
energy, solution energy,
Or
lattice.
Lattice energy.
good. Let us. Good. Now I want to open up a new point. That's a color. Let me explain by the colorful pen. Which colors are there? Colorful. It should be dark also, no? So it's readable. I think some more dark colors. I hope so. Let us see. The color one sees is due to what? We see the different colors: yellow color, red color, brown color, green color, blue color. Is due to what? You also could see, recognize the color due to what? Okay, if I take here the one paper, see this paper has one color. So the yellow color. The yellow color, yes, you are getting yellow color only, no?
Yes, sir.
Yeah. This yellow color is due to what? Or why for this yellow color is there? Paper is yellow, but yellow we are finding why. That's a basic
Reflection.
reflection of what. Okay, now I explain to you. Such yellow paper is there. We are finding yellow color or yellow ink, yellow painting that I did there. If we close our eyes, can we see the color? I'm not talking in terms of mind. In mind we can, because mind can sense anything. By means of eyes. If you close your eyes, can you see?
No.
No.
No,
No. Means keep that logic in mind. If there remains no light, means a dark. Can you see yellow color?
No.
no,
Means important thing to see the color is what should be there?
Light.
Light. And that light should mean just it is I'm saying just don't go on the paint. Okay. It looks like I know it's I. That light should enter through the lenses, and then the retina and all will remain. So retina should what sense. So light when enters through our eyes and our that's a sensors. Eye sensors, you can say, when they recognize retina, then we see the color, means brain and all functioning is there. So entry of that light through the eyes will give us idea about the color. Now everything is not colorful. Now what's the color of the sunlight? And I'm not asking color of the sun. Sunlight I am saying. Yes, what's the color of sunlight? No. Yes, somebody was asking.
No color.
Right, it is no color, or you can say white color, or one can say all colors. Means that white is a combination of all. Colorless, that likewise also we say, means transparent when we find, then colorless we will see. Air is transparent, therefore we say colorless. But if that some white region reflections you find, then you will find it is what the white. So it's just a part of the interaction, the way with which the light interacts with the matter and how it comes. If directly it comes out transparent, then you will find it's a colorless. But perfect reflection is there, then you will find it is what the white. But anyhow, that white light is made up of all colors. Just we say, no, generally rainbow. In rainbow, how many colors do remain? Means poetic point of view. Scientific point of view, it is not true. Yes, seven. Seven. Actually, many colors are there, but from our understanding point of view, seven colors are there. Means seven wavelengths generally we consider. Color is due to that wavelength, but seven wavelengths are not there. Many wavelengths are there. Now that seven wavelengths, seven colors. Suppose if I mix together equal quantity, which color will I find? Is my question clear?
Repeat, sir.
Okay. Rainbow has seven colors. It's our general understanding. So I'm not going to forbid your understanding. I'm not going to take objection about that. Let it be. It's not scientific, but let it be. So seven colors, if I take equal quantity, means in one box, or one container in crucible, no, I'm mixing all 7 colors in equal quantity. Which color will be the result?
White.
Okay, one answer. Any other answer?
White.
White. Good, 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 good. It's a perfect answer. White color you will find. Means to make this concept clear, we can see generally fan of 3 blades. Have you seen the fan of 4 blades?
No.
No. Yes, anybody?
Yes, sir.
Yes, there exist. Fans of 4 blades are there. Even you type on the Google, you will find the images also. Such, now I want to ask you to imagine 7 blade fan, a fan which has 7 blades, and each blade is with the color of the rainbow. Different, all 7 colors are there of equal intensity. So you will find all 7 colors when fan is at 0 speed or low speed. As you increase the speed of the fan, which color will you find? It will look like all blades. The fan blades, no, you will look like. Yes, can anybody guess? Already you have given answer.
White.
Right, it
White.
will be white. But it is not truly only one color. White is not a one color. It is a combination of all colors. Therefore, I'll give you this example, 7-blade fan. But when it fastly move, no, then combination remains. And that combination we understand, introspect. Our brain understands it as white. So sunlight, which is colorless or white, when it falls on any material, here see sunlight, when it falls on any material, then two process possible, maybe reflection or maybe transmission or refraction, you can say. Let any be, anything be, reflection or refraction. While refracting or while reflecting, if all colors do come out, same color, whichever are incidented, all colors reflected or colors transmitted, then result will be white. But all colors are not transmitted. Out of that out of that white, one color is absorbed, and that color suppose is blue. If you remove blue from white and remaining colors whichever will remain, which will be there, mixture of all those remaining colors, what will be the color? Yes, anybody knows? If you remove blue from white, color will be, what's the answer?
Yellow.
Right, color will be yellow. So yellow color for this paper you could see is because the pigment or color of the paper is there, no? That is such a way, or paper quality is such a way that white light all wavelength imparts, bombards out of that one wavelength, blue wavelength, bluish coloration, it absorbs, it is its property, it absorbs, and remaining color means other than blue are reflected, are sent out, and combination of all those colors is blue. That sorry is yellow. One blue color is absorbed, other than blue whichever colors are there, combination is yellow. This yellow is not the one color, it's not a monochromatic. Chroma means color or wavelength. It is with many chromas, many colors are there actually when we see that, but our understanding remains as what? The one color. My point of interest here is color one sees is due to absorption of one or few or many wavelengths. Wavelength means lambda, and lambda is responsible for color. Yes, students could able to understand what I'm saying.
Yes, sir.
Yes, sir.
Yes. So who is responsible for the color? Which phenomenon is responsible for the color? Absorption of light. Now question arises, why for that absorption is there? Why will this paper absorb that blue color? What is the requirement of this paper so that blue wavelength is absorbed? If you consider any material, say this paper is a chemical, molecules are there. Let you take any atom, let you take any element, let you take any compound, let you take any material, means matter. Say is pen is there. I'm holding this pen, means I'm holding the matter, I'm holding the chemicals, I'm holding the molecules, I'm holding the compounds. So when I hold, means what remains outer portion in any molecule, any atom, any element, what is the outer portion?
Air medium.
Which one? Air.
Yes, sir.
No, I'm talking about matter. Air is a matter again. Air is also the matter. Now I'm touch air molecules are there in between. Now I'm touching air molecules. I'm touching air molecules, say N2 molecule, nitrogen molecule I'm touching, or many molecules are there, I'm touching them. But actually I'm touching to whom exactly?
Outermost orbital.
Right, right. When I'm touching this pen or holding this pen, I'm touching the outer coating of the pen, outer portion of the pen. I'm not going inside. So, what is outer portion? Outer portion is, yes, rightly said, rightly said. Help me improve your answer.
Outermost
Outer
orbital.
portion is
Orbital.
orbital
Outermost
is
orbital.
our understanding. But in orbital, who is there?
Electrons.
Right, electrons. So we are touching electrons, or it can be the outer portion where it can interact. So when light incidents, light comes, then this electron finds the opportunity. Electron can get the energy, and if electron gets the energy, then what will happen for the electron? Will electron remain at that place only? Will electron remain with that energy only? What will happen for electron if electron gains the energy? What will happen?
They will excite.
Yes, I could not understand. Repeat.
Excitation.
Excite, electron will go, electron will jump in the higher energy level. What interesting phenomenon is this? See? Any energy, if it comes, suppose it's a one energy level, I say it is E1. It's a second energy level, it is E2, and our beautiful electron is here at that E1, and many wavelengths are coming, many opportunities are coming. Opportunity of physics is there, opportunity of mathematics is there, opportunity of chemistry is there, opportunity of sports is there. All many opportunities are coming towards that what electron, but each opportunity with different frequency, different wavelength, different color, different energy. This electron has one destination, has one target, can go to this energy level. So what this wise electrons does, this electron will accept that energy only which will lead that electron to upper energy level. Suppose if that electron needs energy equivalent to 500 nanometer. See, 500 nanometer is a wavelength, but that wavelength is related to energy, wavelength, frequency, speed. I think the relationship you know. E is equal to h nu, or E is equal to h c upon lambda, Planck's constant, speed of light, and wavelength. So if you know wavelength, energy you can find out, or if you know frequency, then also you can find out what the energy for photon I am saying. Energy for radiation which is coming, no, which electron is likely to absorb, that energy will be what taken. So how wise electron is? Electron will not take any energy. Electron will take that energy only and only that energy, which will lead the electron to the next step. That's a next energy level, E2. If energy is coming of low category, means less powerful, electron will just jump but will not reach to the destination. That's a E2. Electron will not take that energy. That's the perfect calculations, business mind. If that energy is very high, then electron what will think? Electron will take an energy and electron will go a particular more height. So again it will come down. No, it will take that much energy only which is only necessary. Means electron will eat that much food whatever necessary. Only randomly whatever necessary will not take. It's a perfect calculation. So wise is the electron. So electron takes the energy and electron excites. Electron goes to the higher energy level. And electron can take any energy. Electrons present in the pigment of this paper, color of the paper, dye of the paper, what they need? They are hungry for blue photon. They are hungry for blue color. They are hungry for blue wavelength. So it will absorb blue wavelength. So blue wavelength is used, electron will go high, again will return again. So that process is in continuous. That radiations are coming out, but we could not able to recognize those radiations because radiation also different kinds. Emission. I'm not talking here now about emission. I'm talking here about absorption. So whichever the blue color is absorbed is used for electronic transition. What about remaining colors? No use. Paper will say, this pigment will say, the dye will say, I don't want any other color. I don't want remaining colors. So remaining colors will come back. Then combination of remaining color will be our observed color. Students, are you understanding what I'm saying?
Yes, yes, sir.
Yes,
Yes.
sir.
So we are defining now. Observed color is complementary. I think complementary will understand. Complementary to absorbed color. Yellow color is a complementary to blue. which are the wavelength. So accordingly complementary. There's a table also. If this wavelength is absorbed, this color will be there. Means it's a roughly. I said blue color. In blue also many wavelengths are there. So therefore in yellow also various tinges, various ranges of color you will find. Therefore I dared there to say 7 colors in rainbow. Actually many infinite colors are there. Infinite wavelengths are there. But for our eyes point of view, roughly those colors we categorized. In blue also you will find the various colors. Means if you have studied the painting in the computer, the choice of color, then various colors you will find. And dark color, dark green color looks like black, but the dark green color remains. So the intensity is a one thing, and change in the shade of that color is different thing. Change in the color, green, but different wavelength, different color. So that difference in the color that we find is because different wavelengths are absorbed. What the color we see is equal to the complementary to the absorbed color, and absorption is there for electronic excitation or electronic transition. So today I told you one new point. Color one sees is due to absorption of one or few wavelengths, and more important, reflection or transmission of remaining, and most important, combination of those reflected and transmitted waves or colors is our observed color. So we see in the metals also, copper has one color, silver has one color, luster also remains. Luster is also one property. Gold has one color. Again, you can say iron has one color. Chromium also has one other kind of shining. Zinc has separate kind of reflectory or behavior. So different metals also are with different colors. They are with shining. Not only metals, their compounds also are colorful. So first we have to understand why metals are colorful. Shining is there. Metals are characterized by luster. Luster means, are you understanding luster means what?
Yes, sir.
Means metal remains with one particular kind of the shining, which is not remains. So if you take a paper, then that shining will not find. But if you take, say, the metal, then that metal will show you what the one kind of the shining. That shining is nothing but the lustrous property. And the lustrous property is because of the, again, the electronic arrangement. So all those things are related to the electronic arrangement in the system. Let you take it as a metal, let you take it as an iron, let you take as a compound. How is the electronic system? Which wavelength is absorbed? How many wavelengths are absorbed? To what extent wavelength is absorbed? Depending on that, color varies, or strength of the color, intensity of the color, density of the color also do vary. So in short, if I have to say electronic configuration, electronic energy levels is a very important point to understand this concept color. Is this conclusion clear?
Yes, sir.
Yes, sir.
Yes. Now,
Yes, sir.
let us discuss about what the metal. Iron has one color, copper has one color, silver has other color, gold has other color, one particular different elements. So because of their electronic status, electronic arrangement, it varies. When we consider, say, any general metal, then electrons present or electronic energy levels in the metal, we can understand on the basis of one theory. It is called as band theory. It is an extended portion of molecular orbital theory. The molecular orbital theory last semester, which you have studied, even in 12th standard you have studied, that's an advanced application is there. That's a band theory. Means separate bands. That is maybe the valence band, conduction band, how gap is there, accordingly metal, non-metal, semiconductor, their behavior remains. Now my focus is on what? The metal. So their electrons, mean there also quasi-status continuum, their energy levels remain. And in those energy levels also, one particularity remain. So for copper, those whichever the outer electrons are there, they will excite and they will not remain there for longer. They will come out. Means emission, lustrous and all whatever you find now is because of what? The emission. Energy which comes out, energy absorbed is different, and energy which comes out is what? Different. Comes out because of emission is different, and comes out because of reflection and transmission is what? The different one. So there, when such luster shining such remains, no, then at the time that wavelength only comes, that remains some predominant. All other wavelengths also do come, but it remains somewhat predominant. Reddish color comes predominantly more out, and therefore we find copper as a reddish, gold as what? Yellow. It is a concept about the metal. But for compounds, the concept is different. I repeat, I'm explaining colors of the metals. In metals, so different energy levels are there, and closely spaced energy levels are there. Energy status in the iron, energy status in the copper, gold, or silver, or cadmium, or zinc. As metal changes, as atomic number changes, electronic configuration changes, metallic bond and strength changes, the energy levels also changes. But energy levels are in different such a way, everybody is a different character, no? So in copper remains in such a way that when light incidents on that, so the light is all energies are used for excitation, that utilization is done, and then electrons goes up because many energy levels are there, closely spaced energy levels are there, all possibilities are there. While returning down, their behavior is somewhat different than absorption. And while returning, reddish coloration emits more in case of copper, more. Therefore, reddish coloration. Gold, golden color or yellow color emits more. Therefore, it is what golden or the yellow. In case of silver, nearly all colors do emit. It's like a mirror. In case of iron, majority absorption is there and only few colors, so little less shining is there. Shining remains, but somewhat color, grayish color you will find. It's after all combination of the all colors whichever are emitted. So if I have to explain the colors of the metal, then one kind of the explanation will be there, one kind of the logic will be there. That's the energy emitted after absorption of the all colors of the sunlight. Then electrons are utilizing that energy and then returning in the sense of emission. It is in terms of metal. But if we think the compound, say copper sulfate, blue in color, or its solution also, you will find blue in color. Potassium ferrocyanide or ferricyanide, those compounds. Yes, Prathamesh, lecture is there?
Yes, sir. 9:30.
Yeah, okay. Yeah. I stop here. Yes, students, thank you very much for joining the lecture at emergence call. I stop this discussion. Next time we will continue our discussion. Will it do?
Yes, sir.
Yes, sir.
Yes, sir.